Okay, just looking at properties of vector spaces, which is coming up next week, giving you a little something to get into your subconscious and start processing, okay? And not difficult. If you add two vectors, you get a vector. Now that fits our intuitive idea of vectors as either something you could represent by arrows or sums and multiples of the I, J, and K vectors or columns of numbers, right? Okay? If I change the word vectors to polynomials, you can't read that because it's all messed up, but that's what I'm doing. If you add two polynomials, you get a polynomial. Sum of multiples of powers of x, for example. Well, add sum of multiples of powers of x, positive, non-negative powers, right? No negative powers in a polynomial, to another sum of multiples, you get one, okay? So, turns out polynomials can be treated as vectors. Just everything you can do with vectors, you can do with polynomials. The polynomial 0 is a polynomial. It's 0 times x to the 0 power, or 0 times x to whatever power, right? It is a polynomial. Okay, so you have a 0 polynomial just like you have 0 vectors. If you've got a vector, you can change the sign of all of its coefficients, and you get one that you can add. Two vectors you can add to get 0, so you got inverses. Well, you can do the same thing with polynomials. Just change all the coefficients to the other sign, the opposite sign, and add them together, and you get 0, right? So polynomials can do all of this. Okay? So that's one example of a vector space that doesn't feel like arrows. Now, we haven't proven all of the properties. Okay, you got to have a 0, you got to have inverses. Okay, those are pretty obvious, and you got to have closure. If you add two things and don't get the same type of thing, then you can't call those things vectors. Or at least what we want to call vectors are things that have exactly the same properties that our arrows or our columns and numbers do. Okay? Make sense? So that's what a vector space is. We'll look a little closer at it and why polynomials are examples of vector spaces. Matrices are also can be vectors. If I add two 3x3 matrices, do I get a 3x3 matrix? Okay, so this set of 3x3 matrices is closed on addition, right? Is there a 0 matrix that added to any other 3x3 matrix gives us that 3x3 matrix? Sure. Matrix full of zeros added to whatever gives you the whatever. If I change the signs of all the numbers in a 3x3 matrix and add it to the original, I get the 0 matrix. We have inverses. Okay? Now there are a bunch of other properties. You multiply the thing by 5 and you still get 1 and all that. Those are pretty simple properties. But there's a long list of them, about a dozen of the stupid things. Well, we're going to concentrate on the most important ones and the ones that are not always as obvious, okay? And then we get the idea of vector spaces so we can start transforming them and looking at what all the stuff we've learned says about the structure of vector spaces. And it's a big deal. Okay?